coming back to the book, last time we saw, well, in the last class, I discussed some of the properties of sets, and before that, we were looking at the least upper bound property and related related theorems and stuff, and showed that if a set has least upper bound property, it also has the greatest lower bound property. Okay, now to get into more details about the real numbers, before we get to the construction of how actually real numbers are made, let us talk about some properties of what are called fields. Fields. So historically, there are three things called fields, groups, and rings. So fields were discovered first. I say discovered, but more or less invented first by, what's his name? Galva. Okay, and then he discovered groups and rings to study these fields. Now, groups are actually easier to understand, and if you take an algebra course, generally it goes groups, rings, and then fields. However, we are not going to need groups and rings as much, so we are directly jumping into fields as Galois did. Okay, fun fact about Galois, he was one of the greatest mathematicians ever. He died at the age of 21, fighting a duel over a girl. And he knew he was going to die because he was fighting one of the best shooters at that time. And it is still considered one of the greatest losses to the mathematical society that this really brilliant guy who invented a more or less what we know as algebra today died at the age of 21. A lot of his research is published posthumously by his friend, and it took him many years to publish all those papers that Galois had written by then just for fun, more or less. Okay, so fields. Definition. A field is a set F. A field is a set F with two operations on it. With two operations, which we generally call addition and multiplication, called addition and multiplication, and which satisfy the following axioms, which satisfy the following field axioms. Field axioms. Okay, first, let me follow the notation of the book. So, axioms for addition. Axioms for addition. First, if x is an f and y is an f, then x plus y is an f. Okay, let me let you in on a secret. You can think of field generally as the real numbers or the rational numbers, so that if you want examples to think of, these are the easy ones. Rational numbers are a field, but integers are not a field. You'll see some of the properties where it fails. The axioms of addition will work for integers, the axioms of multiplication will not. So if you want counterexamples to think of, integers are a counterexample. So if you want to think when do properties fail, that is where it fails. Addition is commutative. Addition is commutative. What does that mean? X plus y is equal to y plus x for every x comma y in F. Third, addition is associative. Addition is associative. What does that mean? A plus b plus c should be equal to a plus b plus c for every a comma b comma c in F. Oops. Let me just write it in the next line. for every a comma b comma c in F. Okay, so if you're not familiar with the words associative and commutative, and this is the first time you're seeing, this is always what they're going to mean. Commutative means x, any relation of x, y is also satisfied by y, x. Associative always means the order a, b, c, the bracketing does not matter. It matters if it's a, b, c, or a, c, b, unless it's commutative, but the order of bracketing should not matter. Okay. Number 4. This is, okay, let me call these A1, A2, A3, A4, A3, A4. There is a unique element X. F contains an element 0 such that 0 plus x is equal to x. Well, 0 plus x, whatever. 0 plus x is equal to x for every x in F. Okay, now while saying I said unique, while writing down I did not write unique, I will leave that as a proof for you. Here's the way to prove it. I'm going to leave it to you to complete, but take an element y. Okay, suppose it is also acting as a 0, right? Suppose that is also acting like a 0, or call it a 0 prime. Then look at 0 plus 0 prime. Write it down in 2 different ways and show that, well, both of them have to be equal. Okay? To every element x, so for every x in F, there exists a minus x in F such that x plus minus x is equal to 0. So the natural numbers do not satisfy this property. Only the integers satisfy this property. Okay? And so if only these many properties are satisfied, it is called a group. Okay? So as I said, you go groups, rings, and fields. This is what it means to be a group. Not that we are going to use it anytime soon, but in case you're interested, that is what are called the group axioms. Then axioms for multiplication. Axioms for multiplication. First, M1. If x and y, well, if x belongs to F and y belongs to F, then x multiplied by y belongs to F. Okay, so I'm going to denote multiplication by dot. M2, multiplication is commutative. Multiplication is commutative. That is to say, x multiplied by y is equal to y multiplied by x for every x comma y in F. Now, if you have seen matrices before, you might know that multiplication in matrices is not commutative. A matrix A multiplied by matrix B is not always equal to matrix B multiplied by matrix A, which clearly implies that matrices do not form a field. Okay? Multiplication is associative. Well, what does that mean? X multiplied by y all the way multiplied by z is equal to x multiplied by y multiplied by z. Order of bracketing should not matter. For every x comma y comma z in F. M4. F contains an element 1. F contains an element 1, which should not be equal to 0. Okay, this is important, such that 1 times f is 1 times x, not f, 1 times x is equal to x for every x in f. So 1 times x is 1, so 1 is the multiplicative identity, 0 is the additive identity, and they should preserve the element, right? And M5, if x belongs to f and x is not equal to 0, right? Then there should be a multiplicative inverse. There exists an element 1 over x in f such that x times 1 over x is equal to 1. Once again, this element is going to be unique. How do you show that it's unique? Call two elements x and y, 1 over x and maybe 1 over x prime, right? Such that x times 1 over x is 1, x times 1 over x prime is 1. Then look at 1 over x prime times 1 over x. Can you show that that tells you both the elements are equal? Okay, and the final property is called the distributive law. The distributive law. And this tells us how addition and multiplication interact with each other. The distributive law says x multiplied by y plus z should equal x times y plus x times z for every x, y, and z in f. Okay? We do not need the other way around. We do not need x plus y times z to distribute. Only one of them has to distribute over the other. So this is slightly different from union and intersection, which the distributive law holds for both operations. Here the distributive law only holds for multiplication distributing over addition. Okay? So, note, generally, you use shorthand notation for some things. Generally, one writes x minus y rather than x plus minus y, x over y, which is equal to x times 1 over y, and x, y, z, which is equal to x multiplied by y multiplied by z, and so on, rather than, x squared is equal to x times x, and so on, so that we have some, let me write down some more things. 2x, which is equal to x plus x, even though intrinsically we might not have a very good idea of what 2 is, we generally write these notations so that we have some leeway. We don't want to write down the symbols too much if we can get away with things. It is generally understood. A very small note that while we will not be concerning ourselves with generally, is true. This is a very special case. Even if 1 is not equal to 0, 2 might equal 0. Okay? So for example, if you know binary numbers, you know that 1 plus 1 equals 0 in binary numbers, right? And you can still create fields over binary numbers. We are not going to be dealing with those in this course, but there is something called binary fields. Or if you're aware of, if you're slightly aware of modular arithmetic, if you look at if you look at all the remainders left by a prime, so that is 0 to p minus 1, those numbers will form a field, except that will have the property that 1 plus 1 plus 1 plus 1 p times gives you 0, right? So even if 1 is not equal to 0, some other number might be equal to 0. We will not be covering finite fields in this course, but just so you know, those exist. Note 2. Field axioms clearly hold. Field axioms clearly hold for Q, right? And so Q is a field. So Q is a field. Okay. And third, although it is not necessary for the purpose of studying fields, we will show that some properties of Q that we are aware of actually exist as results of field axioms. Okay, some properties of Q are a result, direct result of field axioms. Okay, so by proving them now, we won't have to prove them again for real numbers and complex numbers when we do them. By proving them now, we won't have to prove them again for reals and complex numbers. Now, we haven't defined what reals are and what complex numbers are so far, but we are going to do them in a while. So just so you know, even if you're not aware of complex numbers, that is fine. When we do define them, we'll go through them. Okay, so what are these properties that I'm talking about? Proposition, which I will generally write shorthand as PR prop to the n. The axioms of addition imply the following statements. The axioms of addition imply the following statements. First, if x plus y is equal to x plus z, then y is equal to z. B, if x plus y is equal to x, then y is equal to 0. C, if x plus y is equal to 0, then y is equal to minus x. So this third axiom, property is basically what I mentioned about the uniqueness of negative, right? And number 4, negative of negative x is equal to x. I am not going to prove all 4 of them. Okay, I will prove property 1, and I'm going to leave the others to you as exercise. If x plus y is equal to x plus z, then therefore negative x plus y is equal to negative x plus z. Therefore negative x plus y is equal to negative x plus z, which implies therefore 0 plus y is equal to 0 plus z, and therefore y is equal to z. Okay. Parts proof of parts B, C, and D left as exercise. Okay, they are really easy technically. From part B, you can actually just substitute proper from part A, just substitute proper things, and you get part C, B, C, and D. So I'm not going to prove them. I will leave them to you. Proposition. We saw some properties of addition. Here are some properties for multiplication. The axioms of multiplication imply the following statements. Imply the following statements. These statements are exactly similar to statements in the previous proposition, so maybe I should call these proposition 1 and 2. I'm going to call this proposition 2. Proposition 1. Sorry, these look shabby. The writing can be shabby at times. I'm not very comfortable working on a tablet. This is still a new experience for me. Even though I taught it last semester, I do not own the tablet. I only use it during the semester. So I hope things are still readable. If not, I am talking through them. If you're not able to understand either of them, please send me an email asking which parts mean what, or post it on Piazza. I will be glad to answer them. No issues. Okay. First of all, if x is not equal to 0 and xy is equal to xz, then y is equal to z. Second, if x is not equal to 0 and xy is equal to x, then y is equal to 1. Third, if x is not equal to 0 and xy is equal to 1, then y is equal to 1 over x. And fourth, if x is not equal to 0 and, well, then 1 over x is equal to x. These are exactly in correspondence with the previous one. The proofs are going to follow exactly the same way as the previous one. Just substitute multiplication for addition. I'm again going to only prove A and leave B and C to you. If xy is equal to xz and x not equal to 0, then 1 over x belongs to f, right? Therefore, 1 over x times y is equal to 1 over x times z. Therefore, 1 over x times y is equal to 1 over x times z. And therefore, what do I get? 1 times y is equal to 1 times z. Therefore, y is equal to z. A very small note. What I'm doing here with 1 over x written precisely on the left-hand side, this is important because sometimes the commutativity of addition is not always guaranteed. If things are not a field, sometimes the multiplication is not commutative. However, these results still hold if you have the inverse but not commutativity. Okay? So all the results that I've written so far even hold true even if the field even if the set is not commutative in the operation, but the other results hold. Yeah, so proof of B, C, and D left as exercise. Once again, you can simply get them by substituting proper things. Then proposition 3. Okay. Now here are some things that are slightly more interesting. The field axioms imply the following statements. For every x, y, z in F. First, so A, 0x is equal to 0. Sounds trivial, right? However, now these statements so far, what we have written, these are going to be slightly more interesting to prove. They're not completely as straightforward as before. They're still quite easy, so I will leave some of them for you. But these are more interesting in my opinion. And y not equal to 0, then x times y is not equal to 0. C minus x times y is equal to minus of xy, which is equal to x times negative y. And D minus x times minus y is equal to x times y. Okay? Proof A. So first, we used addition. Second, we used multiplication. For the third proposition, we are going to be using the distribution property. So 0x plus 0x is equal to, by the law of distribution, this is 0 plus 0x, which by the first by one of the axioms of addition, 0 plus 0 is actually 0, so 0 times x. Therefore, 0x is equal to 0, because I can subtract 0x from both sides, and I get 0x is equal to 0, and therefore A holds. Proof of B. If x and y are not equal to 0, and and we have xy is equal to 0, then 1 is equal to x times 1, then 1 is equal to 1 over y times 1 over x times y, which is equal to, is that correct? Yeah. So it is easy to see that this is 0. This is 1, right? 1 over x times x is 1. 1 times 1 over y times y. You can use commutativity, but this is just associated with it. Then, but this is 1 over y times 1 over x times 0, which by the previous property is 0. Right? And that is a contradiction. Therefore, x times y is not equal to 0. Let me just phrase this slightly differently. B, if xy is equal to 0, then this happens, right? C. Now, once again, we are going to do minus x times y, we are going to be using distributive property, plus x times y is equal to minus x plus x times y is equal to 0 times y is equal to 0, right? Therefore, by uniqueness of by proposition 1 part C, minus x times y is equal to minus of xy. Okay, the other half is proved similarly, and I am going to leave, actually, let me just, yeah, prove part D. Part D. So proof part D is in the book. It's also really easy from part C. Okay, so I'm going to leave part D for you. Okay, so now we have a field. Okay, we have also defined what an ordered set is. Now we are going to define what an ordered field is. An ordered field F is a field, well, some part of it is going to be extremely obvious. It is a field F, which is also an ordered set. Field F, which is also an ordered set, but that is not good enough. There are some more conditions such that some properties hold true. The order should work with the field axioms, right? Otherwise, it's just two completely different, meaningless things happening together. These are the things that should be respected. If x plus y is smaller than x plus z, f plus y is smaller than x plus z if x, y, z belongs to f and x smaller than y. Y smaller than z, not x smaller than y, and y smaller than z. Okay. Another way is to say that if y is smaller than z implies x plus y is smaller than x plus z for every xy. And second, xy is greater than 0 if x belongs to f, y belongs to f, and x greater than 0, y greater than 0. So it is an ordered field. We are going to give it some sort of idea of what it means by something to be positive, what it means by something to be negative, and the product of positive numbers should be positive. In fact, we are going to call something positive. If x is greater than 0, we call x positive. We call x positive. And we call it negative. If x is smaller than 0, then x is negative. X is negative. Okay? So both of things are going to work as you would expect them to work in rationals or reals, right? Things that you hold, things that you assume should work, do work. Okay? So all familiar rules while working with inequalities that you are work in every ordered field. Work in every ordered field, right? So multiplication of positive numbers is positive, multiplication of two negative numbers is positive. All of these things work as you expect them to. Okay? Okay, then Now that we have put some order on our field, let us look at some more properties. Proposition 4. Now we have order. The following statements are true in every ordered field. The following statements are true in every ordered field. A. If x is greater than 0, and then negative x is smaller than 0, and vice versa. And vice versa. Okay? B. If x is greater than 0, and y is smaller than z, then xy is smaller than xz. So multiplication by a positive number respects order. C. If x is smaller than 0 and y is smaller than z, then multiplication by a negative number reverses the order. Xy is smaller than xz. D. If x is not equal to 0, then x squared is greater than 0, and in particular 1 is always greater than 0. Whatever happens, you can always say that 1 is greater than 0. And E, if 0 is smaller than x is smaller than y, then, well, 0 is smaller than 1 over y is smaller than 1 over x. Okay? Proof. These are slightly more complicated than the previous ones, but not too complicated. First, if x is greater than 0, then, well, 0 is equal to x plus negative x, right? Well, this is greater than negative x plus 0, or 0 plus negative x. Then 0 plus negative x, right? Because addition preserves order, and so this is greater than negative x. Similarly, if x is less than 0, then 0, which is equal to x plus negative x, is smaller than 0 plus negative x. My bad, this should have been an equal. And, well, this is equal to negative x. Right? Easy peasy. Second, if x is greater, if y is greater than, if z is greater than y, then what does that mean? Well, then z minus y is greater than 0, right? Well, how to prove that? Well, z minus y is greater than y minus y, which is greater than 0. So z minus y is positive, right? Well, x is greater than 0, z minus y is greater than 0. Therefore, x times z minus y is greater than 0. Therefore, xz minus xy is greater than 0. And therefore, xz minus xy plus xy, which is equal to xz. Well, let me just maybe write that down. Is greater than 0 plus xy, and therefore xz is greater than xy. Maybe more steps than required, but that's the more stringent and streamlined proof. Well, by part A and part, not, this looks like an E rather than a C. C. by part A, B, and proposition. What was this? Proposition 3C, I think. I have that negative x times z minus y is equal to negative x times z minus y is greater than 0. Therefore, x times z minus y is smaller than 0, and therefore xz is smaller than yz. So I don't have to do the complete proof. I can use properties that I have proven before. If x is greater than 0, then x times x is greater than 0, therefore x squared is greater than 0. If x is less than 0, then negative x is greater than 0. Therefore, negative x times negative x is greater than 0. And therefore, x squared is greater than 0. Okay? This is by proposition. Which one is this? Proposition 3, maybe? Yeah, proposition 3D. By proposition 3D. Right? And now for the final part C. Final part E, I mean. If y is greater than 0 and x is greater than 0, I'm only going to prove this case. I'm not going to bother about the negative case. I have this, then 1 over y times, actually, let me say this. If y is greater than 0, and let's suppose some v is greater than 0, greater than or equal to 0, actually I want it less than, v is smaller than or equal to 0, then y times v is smaller than or equal to 0, right? Because v is negative, so it's going to reverse the order, but y times 1 over y is equal to 1 is greater than 0, right? In particular, this is true because 1 squared is 1. Therefore, 1 squared is equal to 1 times 1 is greater than 0. Direct consequence of this is 1 is equal to 1. 1 squared is greater than 0, which is 1 times 1, which is equal to just 1, sorry. So this is greater than 0 from the previous part, and therefore 1 over y is greater than 0. Great. I have shown that 1 over y is greater than 0. Similarly, 1 over x is greater than 0, right? Now, multiplying both of them by the inequality x over y, I get 1 over what do we want? Right. So I have x is smaller than y, and I multiplied both sides. Therefore, 1 over y times 1 over x times x is smaller than 1 over y times 1 over x. Oops. 1 over x times y, and here the commutativity is important. Therefore, 1 over y is smaller than var x as required, and that proves the final property. Okay, and I am going to stop this video right here, and we will make another video starting by looking at properties of real numbers and then defining complex numbers. So this is the properties of what is an ordered field and the properties of it. We'll start looking at real numbers in the next video. That's all for this one.